Alrighty, so this video is going to introduce you guys to the concept of rotational symmetry and what that means. So rotational symmetry is when I'm going to turn a figure about its center, not the center of the graph, just the center of the figure, and it will turn back onto itself. So what that means is after a rotation, it's going to look like the figure never, ever rotated on its own. For instance, if you draw in a star, this star can be rotated so it looks just like this. Watch, I can start to turn it. Oh, look at that. It looks like it was never rotated. I could do it again. Wow. Yeah, so that star has rotational symmetry because I can turn it so it looks just like that before it gets turned. Not all shapes have rotational symmetry. For instance, this right triangle does not have rotational symmetry because when I start to turn it, watch this. So I've drawn this right triangle. I start to turn. When does it look like the initial figure? Turning. I keep going. And that is when it looks like the original shape. The problem is that's how it started. So if it has to be turned 360 before it looks like it started, it does not have rotational symmetry. So this triangle does not have rotational symmetry, but the star does. So to help us out with our rotational symmetry, what we're going to figure out is order. Order has to be one of those things that we're going to talk about. This is the number of times a figure can be mapped onto itself in one complete rotation. So for instance, this star, it maps onto itself here, 1. It maps onto itself there, 2, 3, 4, and then back to the original spot, 5. I know it said it doesn't have rotational symmetry if I go all the way around, but orders you have to count the original spot. The shape next to it is called a heptagon. It has 7 sides, if you remember. So we can turn it once, twice, 3 times, 4 times, 5 times, 6 times, 7 times, and it will look just like that. So it has an order of 7. Once again, the star has an order of 5. The heptagon has an order of 7. And the triangle, if we look, it doesn't, if I turn it to here, does it look just like that? No. If we match those corners up, no. So it only has an order of 1 because I have to turn it 1 complete time to get it back to the start. And if it has an order of 1, it does not have rotational symmetry. Okay, so order is how many times I can turn a figure and it maps onto itself perfectly in 1 rotation. It's on there twice. I don't need it on there twice. So let's just jump, boom, boom. So what we're going to do with that order is we're going to help us use that order to find the degrees in 1 rotation of rotational symmetry. Okay, so we're going to start by finding the order on this star. So I'm going to show you how it happens. So the star, we said it has an order of 1, 2, 3, 4, 5. It has an order of 5. I can turn it onto itself 5 times in 1 turn. So we're going to take 360 and we're going to divide that by the order, and that answer is how many degrees in every turn. So 360 divided by 5 is 72. What that means, when we turn the star 1 time, every time I turn that star, it is 72 degrees. The degrees in 1 rotation is 72 degrees. When we take the heptagon, well, we already said, I'm going to count the order again. Let's count the order again. We said it has an order of 1, 2, 3, 4, 5, 6, 7. So the order we said is 7. So if we do 360 divided by 7, because the order is 7, so 360 divided by 7 gives me 51.4. I'm going to round it to the nearest 1/10 of a degree. What that means, every time I turn that heptagon, 1 turn to map onto itself is 51.4 degrees. Every turn is 51.4 degrees. And then we said the triangle has an order of 1. So 360 divided by 1 is 360. And as we can see, that is one complete rotation, so it does not have rotational symmetry for the triangle, but these other ones do. 51.4 and 72. That's how many degrees is in each rotational symmetry. Every click, one turn is this many degrees for the star, 72. For the heptagon, it's 51.4. Well, what if I want to find all the degrees of rotational symmetry? What we're going to do is we're going to add up all the degrees in one rotation, which we just found, 360 divided by order. That's one rotation until we get up to 360, but then we don't count the 360. So for the star, what we said is let's find the degrees in one rotation. The degrees in one rotation is 360 because that's all the way around, divided by the order, and for the star it was 5, and we said it was 72 degrees. So 72 degrees is one rotation of the star. Well, now I'm going to add 72 to itself until we get to, and I'm going to keep doing that until we get to 360. So 72 plus 72 is 144, plus 72 again is 216, plus 72 again is 288. Let me scroll down. Is 288. And then add that to 72 again, and we'll get 360. Well, like I said, when we get to 360, it doesn't count, so we cross it off. So all the degrees of rotational symmetry for this star is 72, 144, 216, and 288. But the degrees in one rotation is 72. All the rotations, 72, 144, 216, and 288. Well, we already said this guy doesn't have rotational symmetry, but if we were to do it, we would do 360 divided by the order, which we've already done, and we get 360. Well, I add 360. It's already 360, so we can see it does not have rotational symmetry. All right, so I hope you took good notes, and if you got any questions, remember to come in and ask your teacher, Patriots, and we will see you when we see you.